Hey there. So, you've handed us Chapter 8 of Deep Learning with PyTorch Step-by-Step by Daniel Voigt-Godoy,
Okay.
which means, obviously, we're diving into sequential data.
All right.
And this is one of those areas, at least for me, where it's like you can go from 0 to 60 really quickly
Yeah.
in terms of the complexity. And
Absolutely.
suddenly we're talking about, stock prices and language translation and
Yeah.
even like,
Text generation.
text generation, right? Like predicting what you're going to type next.
Right.
But it all boils down to this idea that the order of the data actually matters now. It's
Right.
not just
Yeah.
individual data points in isolation.
Yeah. Up until now, we've mostly looked at data points kind of in isolation, right?
Right.
Like, here's our data point.
Yeah.
Let's analyze it.
And now it's like, wait a minute, there's a before and an after, and that
Right.
actually
Yeah. There's a story. There's a sequence.
changes things.
And that sequence actually influences how we interpret
Yes.
the current data point.
Okay, I love that. So it's like the difference between, I don't know, like looking at a pile of ingredients versus actually following a recipe.
Exactly. Yeah. It's like you give me flour, sugar, and eggs. I don't know what to do with that.
Right.
But if you say, first mix the flour and sugar, then add the eggs, now we're talking, right?
Now we're cooking.
Exactly.
So how do we teach a model to kind of read data like a recipe, like to understand not just the individual words, but like the story they tell together?
Right.
And this is where the book introduces, the concept of recurrent neural networks, or RNNs.
Yeah.
And it seems like all of a sudden we're giving our models like a serious memory upgrade.
Yeah, that's the key difference here, memory.
Yeah.
It's like, imagine trying to understand a conversation if you could only remember the last word someone said.
Right.
It'd be pretty difficult.
Yeah, it'd be impossible.
RNNs, they have this hidden state, right?
Right.
And that hidden state evolves as you process each word, each data point in the sequence.
So it's like taking notes as you're listening to the conversation.
Exactly. Building up a richer understanding as you go.
So instead of each input starting from scratch, it's like the RNN is saying, hold on a second, I remember what came before this.
Exactly.
And that changes how I see this new piece of information.
100%.
Okay.
Yeah, so the context actually matters now.
That's huge. And this ability to learn from the past, I mean, it seems like that would be essential for any task that involves understanding, the flow of information, the context.
Absolutely. Think about something like language translation.
Okay.
Knowing the previous words in a sentence drastically changes how you might translate the current word.
Right.
It's really context dependent.
It's like those detective shows where they have that big evidence board with all the strings connecting the different clues, right?
Exactly.
Like each new piece of information gets added to the web and suddenly
You start to see the bigger picture.
creates a bigger picture.
Exactly.
But how does this hidden state actually work? Right. Is it literally like a giant notepad in the model's, metaphorical head?
Not quite a notepad. It's more like,
Okay.
How to put this?
Yeah.
It's a vector, right? So a set of numbers
Okay.
that captures what the RNN has learned from the sequence so far.
So it's not remembering the entire sequence verbatim, but it's like compressing the essence of it?
Exactly. It's like a summary
Yeah.
of everything it's seen so far.
Got it.
Yeah.
And that summary is constantly being updated.
Yes, constantly evolving.
Okay. The book uses this really clever example of classifying how a square is drawn,
Okay.
like whether it's clockwise or counterclockwise, just based on the sequence of its corners.
Yeah, it's a simple example, but it illustrates the point beautifully.
I mean, that seems almost too simple.
Right.
How can an RNN figure that out?
Well, imagine feeding the RNN the coordinates of each corner, one by one.
Okay.
With each corner, that hidden state gets updated, right? It's almost like the model is drawing the square along with you, in a way.
And so, by the end, that final hidden state.
Represents the entire drawing motion.
Okay, so it's like each drawing style, clockwise or counterclockwise, has its own unique path through this hidden state space.
Exactly.
And the RNN learns to distinguish between those paths.
Exactly.
That's really cool.
Yeah, it is elegant, isn't it?
It is.
And this whole idea, right, of the hidden state evolving over time, that's core to how RNNs work, whether we're talking about analyzing stock prices,
Right.
predicting the next word in a sentence, or even composing music.
It's like this really versatile tool.
Exactly. It can be applied to so many different domains.
But, like any good detective will tell you, sometimes you need a bigger notepad.
Yeah.
Right?
Sometimes the case gets a little more complicated.
Like a much bigger notepad.
Right. Exactly.
And the book mentions that basic RNNs, they can struggle with these longer sequences.
They do. They do.
And that's where GRUs and LSTMs come in, right?
Exactly.
What's so special about these kind of souped-up RNNs?
So it's not just about having more memory.
Okay.
It's about having smarter memory.
Okay.
Right? It's like, imagine reading a novel.
Yeah.
And trying to remember every single detail.
Right. It's impossible.
It would be overwhelming.
Yeah.
You wouldn't do that.
No.
You would try to pick out the key plot points.
Right.
The turning points that change the whole story.
The things that really matter.
Exactly. And that's what GRUs and LSTMs excel at.
Okay.
They're like adding a highlighter to our model's toolkit.
Okay.
Allowing them to focus on the most crucial information, even across long sequences.
Okay. Color me intrigued.
All right.
So let's break down GRUs and LSTMs.
Let's do it.
What makes them so good at separating the signal from the noise?
Yeah, let's get into the nitty-gritty.
So we've got these longer, more complex sequences.
Right.
And it seems like just adding more memory, like giving the model a bigger notepad,
Yeah.
isn't always the answer.
No, it's not just about the amount of memory.
Yeah, okay.
It's about how you use it.
So how do GRUs and LSTMs actually do that?
The key is these things called gates.
Okay.
And you can think of them like control valves
Okay.
that regulate the flow of information.
Within the model.
Exactly.
Okay.
So GRUs, they have two main gates, the reset gate
Okay.
and the update gate.
And what do those do?
So the reset gate,
Oh.
that's like deciding how much of the past information to forget.
Okay.
And then the update gate controls how much of the new information to let in.
Oh, okay. So it's like the reset gate is saying, all right, we're starting a new chapter.
Exactly.
And maybe we can forget some of the details from the last one.
Exactly. Like, do we really need to remember what everyone was wearing on page 3?
Right. And then the update gate is like, hold on, this new piece of information, this is important.
This is crucial.
This is going in the cliff notes.
Exactly.
This is what I need to ace the test later.
100%. And the cool thing is, these gates, they're not fixed.
Okay.
They're learned by the network during training.
So it's like the model is learning its own memory strategy.
Exactly. It figures out what to remember and what to forget based on the data it's seeing.
It's like giving the model the ability to not just read, but like annotate the text and highlight the important passages.
That's a great analogy.
But then we have LSTMs,
Yeah.
which sound even more sophisticated.
They are, in a way.
Okay.
They were actually developed before GRUs.
Oh, really?
Yeah, they're like the grandfathers of gated RNNs.
Okay.
And they take this idea of gating to a whole other level.
Okay.
They introduce this thing called the cell state.
Okay, I've heard of this. The cell state, what is that?
So it's like a dedicated notebook
Okay.
where only the most crucial long-term memories are kept.
Okay, so it's like separate from the hidden state.
Exactly. The hidden state, that's like your working memory
Okay.
for the immediate context.
Okay.
But the cell state, that's like the archive.
So the hidden state is like what's on your desk right now that you're juggling.
Exactly.
But the cell state is like what's filed away.
It's the stuff you put in the safety deposit box.
Exactly. For safekeeping.
On that cell state, it has its own set of gates,
Okay.
protecting it, making sure only the most important stuff gets in.
So that's how LSTMs can remember information over like really long sequences?
Exactly. They're the long-distance runners of the RNN world.
Okay, this is amazing, but it also sounds kind of complex.
It is. There's no denying that.
Is there a downside to all this? Like computationally?
So there's always a trade-off, right?
Okay.
LSTMs, they do have more parameters than GRUs or simple RNNs
Okay.
because of those extra gates and the cell state.
So they might be a bit slower to train?
Yeah, potentially.
Uh-huh.
But for tasks where understanding those long-range dependencies is absolutely crucial,
Okay.
like natural language processing,
Oh, yes.
speech recognition,
Right.
the performance gains are often worth it.
It's like sometimes you need a more powerful tool.
Exactly. You wouldn't use a hammer to build a house.
Right.
You'd use a whole toolbox. And that's kind of how I think about these different RNN architectures.
So we've got our basic RNNs, our GRUs, our LSTMs.
Right.
But before we get lost in like, which model reigns supreme,
Yeah.
I want to talk about a practical challenge that I feel like comes up all the time with real-world data.
Okay, what's that?
Sequences that aren't all the same length.
Ah, yes, a classic problem.
Right. It's like trying to build a tower out of Legos where some of them are twice the size of others.
Right, you can't just stack them up willy-nilly.
Exactly. So how do our models handle that?
So we have some techniques for that, and they all involve making our data play nicely with neural networks' love for fixed-size inputs.
Okay, so we need to impose some order on this chaos.
Exactly. A little bit of structure never hurt.
So what's the go-to method? How do we tame these unruly sequences? So how do we impose some order on this chaos of different size sequences? What's the go-to method?
Yeah, so one common approach is padding.
Okay.
And you can think of it like, imagine if you're trying to line up books of different heights on a shelf.
Okay.
You might add some spacers to the shorter ones.
Right.
So that they all reach the same level.
To make it look neater.
Exactly. And we do something similar with sequences.
Okay.
We add these dummy data points, usually zeros,
okay,
to the shorter sequences until they match the length of the longest one in the batch.
So it's like adding blank pages to the end of a book.
Exactly.
To make it fit on the shelf.
Yeah, it's not a perfect analogy, but you get the idea.
Right. Right, it makes sense for creating these uniform batches, but doesn't that introduce unnecessary noise into the data?
Yeah, that's the downside.
Our models probably don't want to waste their time analyzing those blank pages.
You're absolutely right. Too much padding can actually dilute the information in the actual sequence.
Okay, so what's the alternative?
So there's a more elegant solution called packing.
Okay.
And instead of padding, we essentially concatenate all the sequences in a batch.
So we're just stringing them all together.
Exactly. But here's the key difference. We keep track of their original lengths.
So it's like we're stacking those books of different heights one after the other.
Right.
But we're not worried about them lining up perfectly.
Exactly.
But how does the model know where one book ends and the next one begins?
Right. So that's the crucial part. We provide the model with that information.
Okay.
By telling it the length of each sequence within that packed batch.
Okay.
We allow it to process each sequence individually.
Got it.
And it can ignore the gaps that would have been filled with padding.
Okay, that's much cleaner.
It is. It's a much more efficient way to handle variable length sequences.
It's like giving the model a table of contents for the batch, so it knows exactly which pages belong to which book.
Precisely.
Okay, so packing sounds like the way to go. But I imagine working with these packed sequences requires some adjustments to our code, right?
Yeah, you need to make sure your data loaders are set up to produce these packed sequences.
Okay.
And your model needs to be able to handle them as input.
I see.
But the good news is PyTorch provides all the tools you need.
PyTorch to the rescue, as always.
Exactly.
Awesome. Well, this has been an incredible journey, I feel like. We've gone from the basics of RNNs to their more powerful cousins, the GRUs and LSTMs.
That's a whole family.
And we even touched on this idea of 1D convolutions, which I always thought were just for images, but it turns out
they have their uses in sequence modeling, too.
They do. It's amazing how much this field has evolved, and it sounds like it's still rapidly evolving.
Oh, absolutely. There's so much more to explore.
Which is always exciting.
Yeah, it's a really dynamic field.
So for those of you listening, as you continue your own deep dive into the world of sequences, think about this. How can these models be applied to even more complex tasks? What new breakthroughs are on the horizon? Because it really seems like the possibilities are endless.
Absolutely. The future of sequence modeling is incredibly bright.